Okay, so now we're going to look at different example problems for dealing with the integration of exponential functions and functions with an x to the negative 1. So, so we have the integral of e to the 3x dx. Well, when we integrate e to the 3x, we keep our e to the 3x, we add c, but we have to multiply by the derivative of this function, which is a constant, so this is a special case. We divide by that constant, which is going to be 3, or we multiply by 1/3. So like when we take the derivative going forward, we would end up with, e to the 3x still. We multiply by the 3 times the 1/3 goes away, and then the derivative of c becomes 0. So that's what we end up with for our answer. Now, let's say we have the integral of 8e to the 5 minus 4x dx. Well, similarly, we're going to end up with, we have the same thing as before, so we're going to have 8e to the 5 minus 4x. We then have to divide by the derivative of our inside, or the operator on x, which is negative 4. So we can divide by negative 4 or multiply by 1 over negative 4. 1 over negative 4 times 8 is going to give us negative 2. Sorry, that's the plus c. So negative 2e to the 5 minus 4x plus c. So the one thing you want to keep in mind is you don't change the exponent with e, just like you don't change the inside of a trig function. Now let's look at an example where we're going to be talking about x's to the negative 1s. How would we deal with a situation like this? This problem, the integral of the quantity x plus 5 squared over x dx, we can't take the integral of it in this form. We don't know any rules to deal with this. So the first thing that we need to do is we need to expand this, break it apart. So we would get on the top x squared plus 10x plus 25 over x dx. Okay, so now we still haven't learned any rules to have to deal with this. We've got to think of this as 3 separate fractions. And if we do that, we then can find out that we can integrate this. So we're going to end up with, this is the same thing as the integral of x squared over x plus 10 over x plus 25, excuse me, 10x over x plus 25 over x, and that whole thing dx. Again, we still have not learned any rules to deal with this type of issue. We've got to further simplify. So when we have x squared over x, we need to simplify that. Well, x squared over x is going to make x. 10x over x is going to make 10. And 25 over x is going to be, we're going to leave it as it is, okay? Because we have learned a rule for this. So when we integrate this, we have the integral of x is going to be 1/2 x squared, or x squared over 2. The integral of 10 is going to be 10x. And the integral of 25 over x squared, we're going to, or 25 over x, we're going to talk about with it. Dx. This is the one part that's left over. And of course, we're going to have a plus c. Well, this part right here, we learned that we learned this rule that the integral of 1 over x dx is the natural log of x plus c. Well, we don't need the plus c part. We've already accounted for that out here. It's going to just be some extra number. So if the integral of 1 over x dx is the natural log of x plus c, then this here, what we can do is we can convert this. We can say, okay, well, because this 25 is just a multiplier, we can move, oops, excuse me, we can move it out front. So it's going to be 25 times the integral of 1 over x. And so 25 times the integral of 1 over x, because we know that this part up here, we can replace it. And so the integral of 1 over x is the natural log of x. Again, we said the plus c was over here. So your whole answer here is going to be the 1/2 x squared that comes from the integral of x. We have the integral of 10 is 10x. And the integral of 25 over x is going to be 25 natural log of x's. And then we have the plus c at the end. Okay, so let's look at another example here. We have the integral of 12 over 3x minus 4. Okay, so we know that since we have x to the negative 1 as a power on the bottom, we're going to end up using our natural log function. But we've got to adjust our equation to make sure that we are dealing with this in the right way. So this is the same thing as the integral, as 12 times the integral of 1 over 3x minus 4 dx. Well, because the derivative of the bottom, the multiplier on the bottom is 3, we can't do the natural log part yet because that has to be represented on the top. That has to be represented up top. So what we're going to do here is this. We are going to replace the 1 with the 3. Now that is 3 times what we just had. So in order to account for that, we are going to divide on the outside by that 3. So overall, we end up with 12 over 3, which is 4, times the integral of 3 over 3x minus 4 dx. So now we can actually go forward and find our integral. So we're going to have 4 on the outside. The integral of this is the natural log of 3x minus 4 plus c. So this has given us the ability to deal with different problems. Always take your original coefficient, move it outside, and then adjust, like we did over here, like we did right up here, adjust for whatever the derivative of our denominator is going to be. And this is when we have x to the negative 1, or we have a x to the 1 in the denominator of our problem. Now, what if we have the same power of x on top and bottom, but we can't simplify it? We do not know a rule how to deal with that. You can't just move the x's out front. You can't do the same thing because it's an x. It's a variable. You can only manipulate and move around coefficients. So what I suggest doing is doing a little bit of rewriting to help us out. Well, the only thing that I can cancel out an x minus 3 with is an x minus 3. Okay, so how can I get this done? Okay, what I need to do here is, let's think about this like this. What if I had x minus 3 in the denominator? And let's say I had an x minus 3 up here. Well, what would I have to add or subtract on in order to make x plus 5? Well, in order to make an x plus 5, I'm going to have to add 8. If this is the same thing, I've rewritten this in this way to help myself out. Well, this is a good thing because I can split this fraction up then into two parts. It makes sense. Now you could have said, why didn't I split it up to begin with? Well, because x over x minus 3, I can't really deal with. It's really no different than x plus 5 over x minus 3. This is very helpful because I can turn this into the integral of x minus 3 over x minus 3 plus 8 over x minus 3, all that to the dx. Well, x minus 3 over x minus 3 is just 1. And then this is 8 over x minus 3 dx. So I can actually deal with this part. Excuse me while I slip to my next slide. I can actually deal with this part now. Okay, so what I'm going to have is this is the same thing as the integral of 1 dx plus the integral of 8 over x minus 3 dx. Well, we learned from the previous part that what I'm going to want to do is I'm going to want to take the 8 and place it outside. So that I can integrate now. Well, now that I have everything nice and separated, this is in a form that I can deal with. The derivative of our denominator is 1, which that is what we have on the top, so I actually don't need to do any adjustments for this problem. So what I'm going to have is just going to be able to evaluate this now. So the integral of 1 is going to be x. The integral of 1 over x minus 3 is, I have to bring the 8 down. This is going to be the natural log of x minus 3. And then I have to add my plus c onto it. So I had to do a little bit of finagling in order to get this to work. But that's what you're going to have to do sometimes. You're going to have to simplify before we actually integrate, because the rules that we know for integration are pretty clear-cut. So you just want to be careful moving forward with some of these problems that you want to try to simplify and make it work. It has to match the definitions that we have, or else you can't do it. That's the point of the definitions. They allow us to do very specific things in very specific situations, and unless we can make it look identical or close enough, then we're not going to be able to do it. And so just be careful anytime you have x's and like multiple x's in different places. That makes things very, very difficult to do because x's and coefficients do not behave the same way when it comes to integration.